So resuming our lecture, here we're going to talk about reabsorption. So once the filtration has happened, what happens next? So here we're looking at a schematic of the nephron, a broader view of the nephron, and what you can see that things are being reabsorbed, taken back into the interstitial fluid and the blood from the filtrate. Now we have things with the blue arrows that are passive transport that are just allowed to come back out, and things with the red arrows that are active transport that we're actively pulling out of the blood. Now one thing that's really important here is this osmolarity of the fluid. Now up at the outer edge of the kidney, at this top of the nephron, you will see that the osmolarity of the fluid is about the same as what filters out of the plasma in the first place. So we're seeing this 300 milliosmol per liter that's the same as what we have. Now the deeper you get into the kidney, into the nephron, the higher the concentration gets. And that's going to be important for being able to pull water out of the filtrate. So we'll talk about how all of that happens. Now, to be able to get things out, we are going to use, as I said, a mix of passive and active transport. Now, this is looking at glucose sodium symport. This is important because, first of all, we want to pull all of the glucose back out of the filtrate and back into the blood, and we also want to get a lot of the sodium back as well. Now here, this is our sodium-potassium pump. That should look familiar. This is exactly the same sodium-potassium pump that we had when we were looking at the nervous system. So what we're doing is we're pumping sodium out of the epithelial cell and pumping potassium in. Now some of that potassium is going to go back out through leak channels. We're not going to worry about the potassium right now. So we're pumping sodium out of the cell and potassium in. Now we have a sodium glucose symport, and that is not going to use ATP, but it's going to allow sodium to fall down its concentration gradient from the lumen of the nephron into the cell and pull glucose up its concentration gradient at the same time. So it's using the energy of sodium going down its concentration gradient to pull glucose up its concentration gradient. And that brings sodium into the cell and brings glucose into the cell, both of them coming out of the lumen of the nephron. Then we have glucose permease on the other side of the epithelial cell. It's just going to let glucose fall right down its concentration gradient out of this highly concentrated cell that the symport has created and into the interstitial fluid and eventually into the blood, taking the glucose back into the system. If everything is working properly, there is very little to no glucose in the urine. When we do find glucose in the urine, that's an indication that something has gone wrong, that there's generally diabetes, and we're seeing so much glucose in the blood that the kidney is not able to pull it all back out of the urine. So here's our nephron. We have that glomerulus that's already happened, and now we're moving into this proximal convoluted tubule and then the loop of Henle. So zooming into the proximal convoluted tubule, at this point we're going to be reabsorbing a lot of stuff. We're going to be reabsorbing glucose like we just talked about. We're going to be reabsorbing amino acids by a very similar process to the glucose. And we're also going to start reabsorbing water and salts. You already saw how we're absorbing salts. Water is just going to passively follow as we reabsorb a whole bunch of stuff, the glucose, the amino acids, and the salts. We're going to decrease the concentration, and then water is going to follow, go out, because now the filtrate is less concentrated than the interstitial fluid around it, so water will naturally flow out to compensate just the same as we've been talking about in the POGO. So we've got this symport that we've been talking about. We're continuing to look at this reabsorption. Now, we get down from the proximal convoluted tubule, where we have all that sort of very specific reabsorption, to the loop of Henle. And the loop of Henle is where that concentration gradient starts becoming really important, because this is where we're going to have reabsorption of water in the descending limb and sodium and chloride ions in the ascending limb. So here we have a bunch of important stuff that's happening for that with that concentration gradient. Now, the really important piece here is that we have countercurrent blood flow. That means that the filtrate flow is going one direction. So we can think about the filtrate flow is going forward, and the blood flow is going the other direction. We can think about the blood flow is going backward. And that means that we start with this low concentration filtrate, that 300, it's been through there, and then it starts going into this very high concentration environment, at which point it is going to lose water just naturally, again, because it's less concentrated than the environment that it's in. So water is going to passively transport out of the filtrate to keep it at the same concentration. Now, once we get down to this highest concentration area at the bottom, we're going to stop allowing water out. Instead, we're going to have ion channels that allow sodium and chloride out. So as it gets less concentrated, water can't leave, but sodium and chloride can, so we allow those back out. And by the time it actually gets up to the top, it's actually going to be less concentrated than it started at, but with a lot less water and a lot less salt. Now, the importance of the blood flow going the opposite direction is that the blood, as it passes by the ascending loop of Henle, where salt is coming out of the filtrate, it's going to pick that salt up. And that's going to make it more and more concentrated as it gets down to this depth. And then as it's coming back out past the descending loop of Henle, the water is going to come back in and match that concentration back to normal. So these countercurrent exchange allows blood flow to become more concentrated as as it goes down, and then less concentrated as it comes up, but in the opposite order from what's happening with the tubule. So that's how we get this flow happening here in the loop of Henle. Now we can look at that, sort of zoom in here, and you can see just sort of at this higher magnification, basically, water coming out in the descending loop and going into the blood, salt coming out in the ascending loop and going into the blood, with the blood going in the opposite direction, becoming more concentrated and less concentrated in the same way, but in the opposite order. All right, so that's what's happening in the loop of Henle. That's a lot of our water and salt reabsorption, so that we're just, remember, an enormous amount of blood is being filtered through this all the time, and if we didn't have this loop of Henle here, we'd just be losing a lot of fluid. So this is just reabsorbing a whole bunch of fluid, so that now we've got a lot less total fluid in the filtrate. But most of the stuff that we pulled out that wasn't like glucose and salts and amino acids, we still got a lot of that in there. And of course, that stuff that's being reabsorbed is going back into the blood through this these peritubular capillaries and this vasa recta that's linked to the loop of Henle, and that's taking it all back into the blood, so that's going back into the body where we need it. So now we come out of the loop of Henle and we go into the distal convoluted tubule. The distal convoluted tubule has a little more reabsorption, But this is where we actually get into secretion, where we're actually sending some of these things that we don't want into the blood actively into the urine. We get rid of some ions and acids here, drugs and toxins that have accumulated in the body. And this allows us to get rid of actively things that we don't want. Now, certain drugs that we take are particularly filtered out through the kidneys, and this means that people with kidney issues can have problems with some of those drugs. Penicillin is one of the most famous ones. It's almost entirely filtered out through the kidneys, and it gets filtered out through the kidneys very quickly. This means that it's hard to maintain penicillin concentration because it's actively secreted. And it also means that people with serious kidney issues have to be very careful about penicillin. So that is reabsorption and secretion.